Have you ever wondered how global warming works? Me too. I'm a professional engineer, and yet I've never seen a definitive explanation of how it really works. I did the homework, and it's pretty interesting. It's also very definitive. It is happening. I happen to teach engineers classes that they need to take for professional development as the years go by to make sure they're keeping up with changes in science and engineering. So I decided to teach about global warming in one of those classes. After I taught it a few times, I looked back on it and said, wow, this is interesting, and it's not that difficult. I think if people have some basics explained to them, they could really understand it. And that's why I put this video together. I think you'll really enjoy it. As you know, the sun shines all the time, and it sends light out into the universe. Some of it is intercepted by the earth. And if you stand in a shadow and then step out of the shadow into the sunlight, you'll actually feel that energy. Those photons that were produced on the sun have traveled 8 minutes, a little more than 8 minutes to get here. They've passed through the atmosphere and they've warmed your skin. Those photons come in different varieties, which we'll talk more about. But we have names for those varieties, and I think you will have heard about a lot of these. I really do. So let's take a look at them. On the left, we have radio waves and microwaves, followed by infrared, visible, ultraviolet, X-rays, and gamma rays. Scientists have created a chart of the number of photons versus their frequency, their vibrations, in everyday sunlight. This is a picture of the solar spectrum. We have frequency along the horizontal axis, and the height is roughly proportional to the number of photons. So you can see the big hump on the left. It shows that mostly visible light makes up the solar spectrum. The black area on the right is infrared light. Now we can get to the fun stuff where the action starts to happen with these photons and situations on Earth. Approximately half of the visible light photons that reach the Earth actually get through the atmosphere and reach the surface of the Earth. Here's a plot showing the solar spectrum on the left that we saw before, and on the right is the spectrum of infrared photons coming from the Earth. So there's a equally big hump there, a lot of photons coming up, but they're at a completely different energy level than the ones from the sun. In these two pictures, we're going to get a surprise. The one on the left is the landscape illuminated by the sun's rays, what we're all used to looking at. The picture on the right is the infrared photons coming off of all those surfaces. Yeah, the Earth glows. We can't see it, but it's giving off infrared photons 24/7. Hey, it turns out that carbon dioxide has been a noticeable component of the atmosphere for at least 1 million years. And we're lucky, because without the carbon dioxide in the atmosphere, it's estimated the temperature of the Earth would be 0 degrees Fahrenheit. Cold. But it turns out that volcanoes, sedimentary rocks, and decaying organic matter have added carbon dioxide to the atmosphere to the point that the temperature of the Earth is balanced out about 57 to 59 degrees Fahrenheit. Obviously colder at the poles, warmer at the equator, but not a bad overall average temperature, and it's allowed much of the water on the Earth to be liquid instead of solid. Let's take a look at the components of the Earth's atmosphere to see how carbon dioxide fits in. Here we have a pie chart showing the components that make up the Earth's atmosphere. Turns out that nitrogen is about 78% of the atmosphere, oxygen is 21%. Jumping over the other gases, carbon dioxide is 0.04% of the atmosphere. So it's a relatively small component. So let's find out how it has the power that it does. Carbon dioxide has 3 atoms, carbon in the middle and oxygen on either end. Here's some ways of depicting the carbon dioxide molecule. The upper left corner is the chemical formula, 1 carbon and 2 oxygens. Then we have to the right and below that we have the carbon in the middle and the oxygens on the outside. And then in the lower right we have the indication that there's a double bond between each oxygen and the carbon for a total of 4 bonds coming out of the carbon. When photons strike a molecule, if they're the right energy, the molecule absorbs the energy. The photon disappears in effect and becomes part of the molecule. When molecules become excited by this energy, they vibrate. And it turns out the structure of carbon dioxide is perfect for the photons coming off the Earth, the infrared photons coming off the Earth. Here's some depictions of the ways carbon dioxide can bend or vibrate. It could be still in equilibrium. On the upper right you see it could bend. On the lower left you can see it can stretch symmetrically, and on the lower right it can stretch asymmetrically. I'll show you these in another manner next. I think you'll understand better when you can see the motions involved. So, if my head is the carbon and these fists are the oxygen, in equilibrium everything's standing still. The oxygens and the can move asymmetrically like this. They can move symmetrically, so they both go out or they both go in, out and in. And then the bending one is a little challenging for me, but here goes. The carbon can go up or the carbon can go down, up or down. So these bonds between the oxygens and the carbon are bending in this one. There you have it. Now this next concept is totally key. This excited CO2 molecule takes its extra energy, forms a photon, and sends the photon away from the molecule in any random direction. When you think about it, about half of the photons are going to go up towards space, and the other half are going to be sent towards the Earth. Let's take a look at this visually. Here we have the sun shining down on the Earth. The small wavy yellow lines are the visible photons coming in. They strike the Earth in these pretty wide photons come off that are in the infrared frequency, and some of them hit CO2 molecules, and they get thrown out in any random direction. But some get sent down back towards the Earth. And when they strike the Earth, they bring their energy with them, causing the Earth to become warmer. We can visualize the atmosphere with these infrared photons that came off the Earth zipping around. In 66 feet, most of the infrared photons will encounter a carbon dioxide molecule, and the process starts again. It's a little more complicated than that because the higher you go in the atmosphere, the thinner the atmosphere, but still, with all that distance, most infrared photons are going to bounce off a lot of carbon dioxide molecules. And the more carbon dioxide we put into the atmosphere, the more that bouncing around happens, and the fewer carbon dioxide molecules that make it into space, taking their energy with them, and the greater the infrared photons that make it all the way back to Earth, bringing their energy and causing the Earth to warm. A better idea of where things might be headed, we can look at the past. When there was no carbon dioxide, the temperature of the Earth is calculated to be about 0 degrees Fahrenheit. In the pre-industrial era, the carbon dioxide concentration was 280 parts per million, and this resulted in a temperature of about 56.7 degrees Fahrenheit. In about 1950, after some industrialization, the concentration of carbon dioxide was in the range of 310 to 312 parts per million, and the temperature on Earth rose a little bit to 57 degrees Fahrenheit. In 2024, ignoring some of the noise, the variations in concentration, a good concentration for that year was 352.9 parts per million, and the average temperature on the Earth was about 59.2 degrees Fahrenheit. So you can see the more carbon dioxide present in the atmosphere, the greater the temperature. This little guy is looking back through his telescope. Let's do the same thing with what we've learned today. Turns out that it can all be boiled down to three major points. Photons from the sun, mostly in the visible light range, impact the Earth. About half the visible range photons cruise through the atmosphere unaffected and strike the surface of the Earth, imparting heat. Everything on the surface of the Earth then emits photons, mostly of the infrared type. These photons travel upward until they encounter a carbon dioxide molecule. Their energy causes the carbon dioxide molecule to vibrate, and the photon is no longer a traveling entity. It becomes part of the energy in the molecule. After a few microseconds, the carbon dioxide molecule emits an infrared photon in some random direction. About half the emitted photons travel downward. The effect of these photons traveling downward means that a greater number of infrared photons make it back to the Earth, and the fewer the infrared photons that leave the Earth and go into space. The combined effect is that the Earth becomes warmer. Now you know how global warming happens. It's just light energy and carbon dioxide molecules. If someone says it's not real, it's not happening, or it's not the result of humans, you just explain what really happens.